Okay, so we're talking about these mappings, and we're talking about nonlinear mappings. So I think it's interesting to kind of step back for a minute and see, well, what is it really that makes these mappings nonlinear? Well, one way to describe that is to describe what makes them linear, and then the nonlinear ones are everything else. Okay, so here's one way to do that. We said when you study linear systems that the fundamental principle or property that linear systems have is this idea of superposition. Okay, that you can superimpose inputs and initial states, and the superposition property holds for linear systems. So again, if we've got some system here, mapping u to y with initial conditions perhaps in there, we could say, well, y is some function of u and the initial state. I'm being a little vague about this. Normally y will depend on not only u at the same time that you're looking at y, but past u's. Usually most systems have memory in them. Most dynamical systems have memory, and so really y at some time is a function not only u at that same time, but all past u's. Okay, but just kind of roughly speaking here, y is a function of u and x0. And so a superposition property on this with respect to the input would be something like f of the sum of two inputs applied to the system. All right, if I take and add two inputs together and put them into the system and see what that does to y, to be linear, we'd have to have a superposition principle that says I could describe the output as the sum of the outputs from the individual inputs. So here's the output I get from applying the inputs separately, and I could get the same output as if I sum those separate applied inputs and the resulting outputs. So that's the same thing as if I put in the inputs together into the system. So that's the superposition principle. We could do the same thing with respect to states. If I had two different initial states, x1 and x2, and I add those together, and I look at the system's response due to that sum of initial conditions, okay, what would you expect to see on the right-hand side here?
F of u of x1 plus f of u of x2.
Yep. Again, it's the sum of the effects of the inputs, in this case the initial conditions, applied separately. Okay, so if your system behaves like this, it's linear. If it doesn't, it's not. Okay? Now, this is a little hard to test because really this has to be true here for all U1 and U2. So it has to be true for more than just any two you pick, but all pairs of inputs you pick. So to test this really is kind of difficult, right? It's hard to test all of them. Particularly if you have, something you're just empirically playing with, right? You put an input to it, you measure the output, see what happens. You give it another input, you look at the output, see what happens. If you don't have a model for the system, that's just purely an empirical understanding of what the system is like, it would take a long time to test this. Okay? You have to test all possible inputs. So you really can't test linearity without a model for the system. Okay? So really, when you think about it, when we're studying these things, what we're really studying are models for things, not the things themselves, right? And so really we're asking questions about the models. Is the model linear or not? Okay, and often we'll even fudge this a bit and we'll develop models for systems we know are nonlinear, but we'll develop linear models for those as approximations because linear is easier to deal with. Okay, so that's the typical thing. So, even if the model is linear, the real system you're dealing with may not be. And so that's a good perspective to keep, because you can fool yourself if you think the model is the real thing. It usually is not. Same is true here. Upside down A is for all. This has to be true for all of these initial states as well, not just two of them. Now, it's actually a lot easier to show a system as nonlinear than to show it's linear. What do I have to do to show a system as nonlinear here? I just have to find one pair of inputs u for which this equation is not true. Okay, that's all it takes to show that this property does not hold in general. So it's actually not too hard to show a system as nonlinear. You just have to find one case that shows the superposition does not work. Okay, another way to do it is if we have the model for the system in the form of differential equations. So let me take the case of a state space model here. Here's a general nonlinear vector field. So if you give me a position in the state space X and an input u, I can tell you how that state will change with time right there. That instantaneous direction it's moving, that's the vector change in the state. And if I look at this over all possible x's, I generate a whole field of vectors. That's why they call it a vector field. Okay. So if I have a general vector field like this, if this was equal to, if I could split this function f up into something that looks like some matrix A times x plus some matrix B times u, where A and B are constant matrices, they don't depend on x or u, okay, then that's a linear vector field. Okay. And likewise, if my output y depends on the state through some function h, may also depend on the input u directly. If I could write that as some constant matrix C times x plus some constant matrix D times u, where C and D don't depend on x or u, then again, that's a linear system. Okay. So I could look at my functions f and h, and I can see if that's that's kind of cool. I don't even have to touch the touch the screen to screw it up. Have to watch out for that. So I can look at those models, these differential equations for my system, and I can see if I can write it this way or not. If I can't write it this way, I know the system is nonlinear. Okay. So it's often pretty easy if I have differential equations to look at the thing and decide if it's linear. Okay.